Hello class. So today I would like to give you some help with answering the questions on Pearson when it comes to answering two sample tests. So the first thing we're going to talk about is the new templates on ELC. So there is a new file now which has templates both for one sample test and for two sample tests. As always, small disclaimer, there might still be typos in them, so please help me find them. If you see something that isn't working, let me know. So why do we have a new templates file? Well, because at this point we have so many different tests to choose from, we actually now have almost 30 different tests in total that you know how to do. So the difficulty here becomes knowing when to use which template, or which test are you actually trying to do. And the questions that guide you in this process are, is this a one sample or a two sample test? Then is it a mean, a proportion, or a variance test? If it is a one sample test, do you know the sigma, which will tell us whether I'm using a z or a t distribution? If you have two samples, the question is, are the sigmas equal? And then in addition to that, you have the question of whether this is a confidence interval and also whether it is two-tailed, lower-tailed, or upper-tailed test. Now I've made you a decision tree to guide you through this process. So let's take it one step at a time. You get a question on Pearson. First thing you ask yourself, is it a one sample or a two sample question? If it is a one sample question, you ask yourself, is it a mean or a proportion question? If it is a proportion question, you go on the tab that does z-tests for proportions. If it is a mean test, you ask yourself whether you know sigma or you don't know sigma. If you do, then it's a z-test. If you don't, then it's a t-test. Now, if you have two samples, if you remember last time's lecture, there are three types of tests you do. There are the mean test, the proportion test, or the variance test. So that's the first question you ask. If it's a variance test, then you use an f-test. If it's a proportion, then you use a z-test. And if it's a mean, you have another question you can ask. Are the samples related or not related? Can you pair them or can you not pair them? If you can pair them, you do a paired t-test. If you cannot pair them, then you actually have one more level of question to ask, and that one is, can you assume that the sigmas are equal? If you can, then you do a pooled variance test. If you cannot, then you do a separate variance test. Both of those are t-tests. Finally, once you know which type of test it is you're doing, you still have to ask yourself whether they're asking you for a confidence interval or if they're asking you for a two-tailed test or a lower-tailed test or an upper-tailed test. Now remember, the way you decide this is going to depend on that test, right? You use the f-test to answer this question. So you may have to do both an f-test and then one of these tests in a question. All right, so let's take a look at them. This is the file that you're going to find on ELC. Now, the first thing you notice is that you still have these four tabs that you're used to. The one for the confidence intervals, the one for the one sample mean, the one for the one sample mean with a T rather than a Z, and the one for the one sample proportion. Now, in addition, I've now added these five other tabs. And again, their names are pretty self-explanatory. Two sample mean pooled variance, that's to make a pooled variance test of the mean on two samples. And similarly for these other names. So you have four tabs for one sample test. One, the first one that is just for confidence interval questions and for sample size questions. And then a tab for means with known sigma, that's a z-test. Means with unknown sigma, that's a t-test. And one for proportions, which is always a z-test. And now the five new tabs, those are a tab for pooled variance test of two means, a tab for separate variance tests of two means, a tab for paired tests of two means, and then one tab for tests of proportions and one tab for tests of variances. This is the tab you're used to. The first one, the one about confidence intervals. Here you have a confidence interval for the mean, with sigma known, with sigma unknown, or for the proportion. All the confidence intervals, you can just get them from this first page. And remember the questions that ask you, how big of a sample do I need to get a certain confidence on my mean estimate? That's where you find the answer to that. And this one is the equivalent for proportions tests. This tab you're familiar with. Again, it's a means test using a z-distribution. Of course, you have three versions of it: two-tailed, lower tail, and upper tail. Make sure you read which one you're using. And as always, the answer pops up here in the bottom. Notice that on that second tab, you also have the confidence interval that pops up at the bottom of your template. So that is slightly redundant with the first tab. The third tab is exactly the same thing, but with a t-test. Remember, that's when you don't know sigma and you have to use an S, a sample standard deviation. Again, you have three versions of it. The two-tailed test is the first one, and then a lower tail and an upper tail. The fourth tab for proportions works the same way. Okay, so here we have the new ones. This is the tab for pooled variance. So that means you're comparing the means of two samples, and you can assume that they have the same sigma. Of course, you have three versions of it: two-tailed, lower tail, upper tail. And as always, that blue area is where you input the data from the question. It's only a little bit more complicated than the previous four tabs because now you have two samples to look at. So you have a sample size, a sample mean, and a sample standard deviation for the first sample, and a sample size, a sample mean, and a sample standard deviation for the second sample. The confidence interval still gets calculated for you. The separate variance test works exactly the same way, except that you assume you have different sigmas. You fill in the exact same information because the difference between the two tests is just an assumption. Do you assume that the sigmas are equal or do you not? That doesn't actually change the value that you have for your estimates of sigma. It just changes the calculations that your template needs to make. Okay, the next tab is the one for paired t-tests. Now remember, a paired t-test is when you can pair up each of the observations from one sample to another observation of the second sample. And what did we say in the last lecture? We said that when that happens, you actually just do a single sample test on the difference. So here what you have is again a very simple set of data to enter. So once again, even though you have two samples, remember you create this one variable d, which is the difference between your two samples, and then you don't have that much data to put in because you're only talking about this one variable d. It's like a two sample test that you've boiled down to a one sample test. Again, you get confidence intervals here. The test for two proportions is not difficult. Again, because you have two of them, you have to enter more data. As previously, what we want to input here are the counts of the samples and the counts of the successes. Remember, the successes are the number of observations that comply with whatever criterion you're looking at. And finally, on tab 9, we have the f-test, the test for the equality of variances. Now remember, we said in the lecture there are only two types of tests here. Either you do it two-tailed or you do it upper-tailed, but you never do a lower-tail test. Now, the only really important thing you need to remember about this test is that the larger variance sample is on top and the smaller variance sample is at the bottom. In this case, you can verify that the one on top has a variance of 67 and the one on the bottom has a variance of 15. That works. That's what we needed. Be careful, it's not about the sample sizes. As you notice here, the sample size is actually smaller at the top than it is at the bottom. It is the variance that matters here. A quick way to ensure that you're doing it right is looking at your F statistic. If it is smaller than 1, then you've done it the wrong way. Here, of course, it's 4.25, so that's fine. All right, now that I've described all of the tabs, let me show you how this works with a few questions. So here is your typical Pearson question. You get this table, and you're going to have to answer a few questions. Before you even start looking at the questions, you could already guess exactly what type of test they want you to do. So take a second here and think about that. Our data has three columns: an ID for the provider, and then their rating for TV and their rating for internet. If you haven't already guessed what type of test this is going to be, let's walk through it together on the next slide. So first of all, is this a one sample or a two sample test? Well, clearly two samples. We have the internet and the TV. Is it a mean, a proportion, or a variance question? Well, we haven't even looked at that yet, but I already know it's going to be mean. Why? Because the samples are paired. They are related. We have two observations for each provider, and this means we can do a paired t-test. So all we need to do now is figure out whether that's a confidence interval, a two-tailed, a lower-tailed, or an upper-tailed. So we read the question. They're asking whether there is evidence of a difference in the mean service between TV and internet. But because we have three columns here, one for TV, one for internet, and one for the provider, we're not just going to do a test of the means of this versus that column. Instead, we are going to pair them, take their difference for each provider, and test mu d. So we know that we are testing mu d, and we know that we want to test mu d equals 0. But mu d equals 0 versus what? Let's go quickly by elimination. Greater than is not the mathematical opposite of equals, so that's wrong. This is also wrong. This is also wrong. And this is not even the right H0. So the only candidates that remain are E and F. But you know how to construct mu d. Mu d is mu1 minus mu2, not mu1 over mu2. And so we go with this one. This is what we need for the paired test. Once you figure that out, that tells you which template you're going to be working with. This one, the one called two sample mean paired. It's a test of the mean with a paired t-test. And because we had an equality sign in our H0, this is going to be a two-tailed test. Now, what do you need to fill this in? Look in that blue box. You only need 5 items. The 5 things I need are the hypothesized difference, the alpha, the sample size, the d-bar, and the SD, the d-bar being the average of differences, and the SD being the standard deviation of differences. The first 2 you get from the question. The last 3 you get from the data, meaning you're going to compute them yourself in Excel. What do I see in the question? We see it's a 0.1 level of significance, so alpha equals 0.1. We see that they're asking for evidence of a difference, so anything different from 0 is a difference, so the hypothesized difference is 0. That's my H0. So what do you do next? Well, you need to compute that D variable. What's the D variable? It's the difference between column B and column C. So let's compute it for the first row and then drag it down. Then what do we need for this D? We need the sample size, the D-bar, and the SD. The D-bar is the mean, the SD is the standard deviation. So you compute them with the 3 formulas you already know: count, average, and STDEV. And now all you need to do is take these numbers and punch them into your template. The question asks you for the t-stat, you read it off the template, and then they ask you for the p-value, you also read it from the template. And of course, because this p-value is low, you can reject. When you reject, it means you have sufficient evidence to reject. Usually they'll ask you a little question afterwards about the assumptions. In this case, the assumption is that the distribution of the differences of the D variable is approximately normal. All right, let's do another one. Here's a question where you have to produce shingles type A and type B. The data in the table is the weight in pounds of a first sample of type A shingles and a second sample of type B shingles. Looking at that question, you already know this is going to be a 2-sample test because you have 2 samples. Then the question says what? Completely analyze the differences between the weights of type A and type B. What do they mean by completely analyze? Well, let's read a little further. It tells us first perform an F-test. This is going to be a two-sample question. It is going to be a mean question, but it says to start from an F-test. So there's going to be a variance question followed by a mean question, because the variance test will determine whether we have to use a pooled variance or a separate variance template. So first we perform the variance test. How do we do that? Well, we just need the count and the variance for both of our samples. We get those from Excel, and then we plug them into our template. Oh wait, what happened here? I have an F statistic that is less than 1. That's no good. Why is that happening? It's because my sample variance here is greater than my sample variance here. I'm dividing a small sample variance by a bigger sample variance. I want the opposite. The largest variance must always be on top. The F-stat is never less than 1. Here, that's much better. We flip them around. And what do we see? Reject the null hypothesis. The variances are not equal. We answer that question in Pearson, and that allows us to move on to the next one, which is the means test. Which means test? Well, we said there was sufficient evidence of a difference in the variances. So what are we going to do? A separate variance test. Pearson actually guides you through that process. The samples are independent and there is sufficient evidence that the variants are different. So you use a separate variance t-test to compare the means. The new hypothesis test is a test of the means, the mu's, and we test their difference against 0. There is nothing to suggest that this should be a one-tailed test, so we do a two-tailed test. Okay, so we know which test we're going to do. It's two samples, mean, separate variance. This is the tab we have. All we need to do is enter the information. And here you see my separate variance test statistic is what I have to input into Pearson, and the exercise is complete. You will see quite a few of these exercises that use both the F-test and then follow with a means test. Okay, so I'm going to post these slides on ELC and you can look at them at your convenience. They have all of the instructions. However, I can also show you on this video how this would be done exactly. So let's take a look at this exercise right here. 9 experts have rated 2 brands of coffee. I already know that this is going to be a paired test. Why? Lots of clues. First of all, I have 9 experts that each rated the 2 brands of coffee, so I can pair them. Same expert, 2 brands. Second clue, all of these mu's have a D there. I know what this D is. This D is the difference variable. So even before I get started, I already know I have to go straight here to the mean paired tab. And even before I look at the data, I know that this is not the correct answer. An unequal sign never appears in H0. So I know it has to be one of these 3. Let's read the question a little more carefully. Is there evidence of a difference? Doesn't say anything about greater than, doesn't say anything about less than, so we're comfortable with A. All right, we need that T statistic. Let's get our data. Open it up in Excel. Here it is. What do we get? We take our D variable. We want it to be brand A, the first column, minus brand B, the second column. Drag this down. And then we just compute. What's the N? What's the mean? What's the standard deviation? Count. N is the count. There's the same, they both have the same count. Average is the formula that helps us with this. And stdev or stdev.s, both will give you the same answer because this is a sample, is the one that gives us our standard deviation. Okay, those numbers are very round. Let's see if we don't have some decimals here. Nope, they are exactly equal to 9 minus 1 and plus 1. Let's plug in those values. The sample size is 9. The D bar is minus 1. The standard deviation is plus 1. The hypothesized difference is 0. Let me just recheck what the level of significance was going to be. 0.05. Let's change this. So what do they want the t-statistic? It's exactly -3. 2 decimals, I'm going to add the 2 zeros because I know Pearson is really finicky about this. And there we go. The critical values, we want 2 decimal places. Let's change this to get 2 decimal places. Minus 2.31 and 2.31. Fantastic. Now the t-statistic is where? It is below this lower value, so it does not fall between the values. Therefore, we can safely reject because there is sufficient evidence. Remember, anytime you reject, it's because you have sufficient evidence to do so. And finally, that question about the assumptions. We've never said anything about skewness or uniform. Assumptions are almost always about normality. Let's do this. One more question, they want the p-value. Let me change those decimals back. They want 3 decimals here. What is the p-value? It's the probability of getting our test statistic or something more extreme. So it's not answer C. It doesn't say anything about equal to or more extreme. This says something about less extreme. Okay, so we have a really good hunch that this is going to be the right answer. Let's make sure it's the probability of obtaining a sample mean difference, right, an SD, at least as extreme as the one that we found. If H0 were true, meaning if the population mean ratings of the brands were the same. Okay, I'm confident. Last question, they want the confidence interval. I just need to read it off of here. Again, let me change those decimals. Don't need to think too much. Minus 1.77, minus 0.23. And we're good. All right, let's do another one for sport. Here, what do we have? I see pies everywhere here in the hypotheses, so I know this is going to be about proportions. Let me directly switch to the correct template. It's the one about 2 sample proportions. What's my H0? Well, only one of these makes sense because they're again asking us about a significant difference. They're not saying anything about greater than, smaller than, so we can go with D. They want us to figure out the z-stat. The template is going to do that for us. Let's switch back to our template and punch in the correct values. N1 is 50, X1 is 10, N2 is 50, X2 is 20. N1 is 50, X1 is 10, N2 was also 50, and X2 was 20. Last thing, let's not forget to check the level of significance. What did they want? They wanted 10%. Let's switch it. Okay, they want a z-stat with 2 decimals. Minus 2.18. A p-value with 3. Okay, this one is easy. 0.0291. Oh no, I got carried away. All right. Okay, our p-value is what? Pretty low, definitely lower than 0.1. So we can reject the null because there is sufficient evidence. And the confidence interval, we got it right here. This time, no worries, they want 4 decimals. Here we punch them in. And they're good. Okay, this should be good enough to help you as a demo. I'm not going to go over all the exercises. Try to do the lab at home. If you're having problems, definitely get in touch with me. I can post more videos like this one. I can run you through the labs. As you see, this is the same thing you just did on your midterm, just now we have more templates to choose from, and you need to think carefully about the type of problem that you're trying to solve. The good news is, this is the end of our hypothesis testing chapter. Next week, we're going to start analysis of variance, or ANOVA. All right, good luck with the labs.